not sure what happened, but I apologize for that. Let me. All right, and I'm also going to put that into the chat real quick. Hopefully everybody's having a good day. So that the document that we're using today is in the chat, and it's also on Blackboard if you want to grab it. Let me put it up here and share my screen. And we're probably not going to finish this document today. So just save it. And then what we're gonna do tomorrow in class is use the examples in the document to discuss some other topics like unit conversions and things like that. So let me share my screen if my computer will cooperate. And let me turn my camera off. Let's see. All right. So we're going to start out at the top with number 1, where it says classify each of the following changes as physical or chemical. You can unmute to chime in. Hopefully that's big enough for everybody to see. Let's look at A. Is steam condensation, which is turning steam back into liquid water. Is that physical or chemical? Excuse me.
Physical.
Chemical.
It's actually a physical change. A chemical change would be something like taking water and ripping it apart into its constituents, or taking water and reacting it with something else and getting a new compound as a product. But going from changing states is a physical change. So you change from liquid to gas, gas to solid, solid to liquid, so on and so forth. All of those are physical changes. And this is a state change. Going from steam to back to liquid water is physical. What about B?
Chemical.
Chemical. Anytime you set fire to something, that's a chemical change. Because when you set fire to something, you are doing a chemical reaction on that thing, and it undergoes combustion. So gasoline is, if you burn gasoline in an engine, it gets converted. The document, Elijah, is on Blackboard under recitation handouts. It's week 2, and it's also in the chat. But if you're on a phone, you're not gonna be able to see it in the chat. So you got to grab it off Blackboard. All right. Let's go to C. What?
Chemical.
Good. Sour milk turning sour is indeed a chemical change, and it has a physical manifestation of that chemical change, in that it may get lumpy, it may smell bad, and it definitely tastes bad. I don't know how many of you have ever tasted sour milk. It's pretty gross. Yeah, it's nasty. But yeah, that's definitely a chemical change. Since you answered that, can you tell me what you think causes that chemical change? Think about it. What's the whole?
I think because
Go ahead.
when the milk sours, it gets like clumpy. So like the calcium in it or something starts to like come together or something. I don't know.
But the other part of that, what's the purpose of pasteurization? When we get milk and we pasteurize it, what's the purpose of that? Anybody know that?
It can be drinkable to humans because don't it have pus in it normally?
Pus, bacteria, all types of stuff. So when milk turns sour, that is a chemical reaction. Normally there's some bacteria or some, and that's when once you open it, then the oxygen starts wreaking havoc on everything, right? So the bacteria that's in that milk, they begin to undergo chemical changes. They begin to react with different compounds in the milk, and so that's when it turns sour. What about D, dissolving sugar in water, chemical or physical?
Physical.
It's a physical change. If you and what you're doing is you're making a what type of mixture is sugar water? We talked about mixtures last week. Two types, right? Homogeneous, heterogeneous. What type of mixture, if I dissolve the sugar in the water to where you can no longer see it, is that homo or heterogeneous?
Hetero.
If you can't see the sugar, it's
Homo.
homogeneous, right? Because it becomes uniform. Remember, it's uniform in its composition. So sugar water is a homogeneous mixture of sugar and water, but it's not a chemical change because the sugar nothing happens to the sugar molecules to convert them into something else. So this is a physical change. All right, what about when you melt gold? What is melting a result of? Oh, let me not say that. What is melting? The process of melting. You're going from what?
Solid to liquid.
A solid to a liquid. It's a state change, isn't it? All state changes are physical. I heard somebody say chemical, right? Melting is it may seem like it because you have to apply heat, that it's a chemical change, but unless you're burning the gold, melting just converts it from a solid to a liquid. If you heat it past its melting point and you start to burn it, then you get different, that becomes a chemical change. But just heating something up to the melting point is a physical change. We're okay with that? Everybody good? Again, we're not going to finish this, but we're going to hit it. And whatever we don't finish today, we're going to finish tomorrow and then probably take our first exam sometime next week, either Wednesday or Friday of next week. All right. Ready? Y'all ready for number 2?
Yes.
All right. It says a 2-liter volume of hydrogen gas combined with 1 liter of oxygen gas to produce 2 liters of water vapor. How does oxygen undergo a chemical or a physical change? Now let me show you this first, right? Because I know it sounds weird, but let's write it out. You got 2 liters of hydrogen. That's the hydrogen molecule. Remember, there are 7 diatomics: hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine, iodine, plus oxygen. And that leads to water. Now, this is not balanced. Based on the law of conservation of matter, you got to balance this equation to make sure it's the same number of atoms on both sides. So if I put a 2 here to make sure I have 2 oxygens on both sides, then that's going to give me 4 hydrogens. So I need to put a 2 here. I know we haven't talked about balancing yet, but you know, no time like the present, even though we're not really having a discussion about it. All right. Is the oxygen on this side? Let me change the color of my brush. Is this oxygen the same chemically as the oxygen on that side? Or is it different? Remember that O2? Can somebody tell me what that looks like? Remember we talked about what that looks like? Anybody remember? Is it not oxygen double bonded to another oxygen? Did y'all forget that fast? All right, what do you think? What does the water look like?
It's one oxygen connected by two hydrogens.
Yes, thank you. What type of bond is that between the oxygen and the hydrogen? Do y'all remember? We talked about this.
Single bond? Single bond?
It's a covalent bond.
Covalent, good. It's covalent. But the covalent bonds to oxygen on the right side are different, aren't they? Because they're to hydrogen and not to another oxygen. Right? Do you see here how the bond is to, in water, is to hydrogen? Is that right? So that oxygen is different now. It underwent a chemical reaction with hydrogen, so it's totally different. So this is a chemical change to oxygen. Yes, no?
Yes, sir.
All right.
Yes, it's a chemical change.
All right, good. Let's go to the next question. It says indicate the SI base units or derived units that are appropriate for the following measurements. So again, remember when we talked yesterday about these base units, there are 7 fundamental measurements, right? There's length, there's mass, there's time, there's temperature, there's luminescence, and the amount of a substance, which is a mole, and there's one other one. Anybody remember the last one? Feel free to go back to your notes, look at the chart.
So can you repeat that question one more time?
The 7, remember yesterday, if you recall, we talked about the 7 fundamental measurements for SI units. And we said that there was length, mass, time, temperature, luminescence, the amount of a substance, which is measured in moles, and there was one other one.
Grams.
That's mass, right? Let me pull the notes up from yesterday. Say that again.
Electric current.
Electric current. Very good. Excellent. 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 All right. So now let's look at the questions. It's asking us for SI base units, right? So SI base units are going to be meters for length, grams for mass, seconds for time, Kelvin for temperature, amps for electric current, moles for the amount of a substance, and then I think it's lumens. Let me go back and look. I don't want to tell you something wrong. I think it's lumens for the luminescence. Let me pull that chart up.
Yes, that's right.
But it's candelas. Sorry. All right. So let's go back and answer the question. So the length of a marathon race, it says 26 miles, 385 yards. What is the unit for length?
Meters.
Meters. Good. So we know that this would actually be measured in meters. Right. And we can calculate that. If you remember, 1 meter is 1.09 yards. So can we calculate yards into meters? Can we convert that? Right. let's try it. If we have 385 yards, we need, what do we need in order to swap out or change units? What do we use to do that?
I don't remember the name of it, but you'd have to put the measurement that you're trying to cross out on the bottom
Good.
underneath the measurement that you want to switch it to.
Good. That's called a conversion factor, right?
Yeah.
So we can put, and I'm gonna run out of room, but this will be times. In the top, we want meters, so 1 meter over what? 1.09 yards. So yards will cancel. And then can somebody divide that real quick and tell me what that is in meters? That should be a little bit less than 385.
I got 353.2.
We'll take it. 353 meters. You said 353.2?
Yes, sir.
All right. We'll take it. All right. So yeah, so that we want that in meters, right? So we didn't do the miles because we haven't talked about that yet, but we can do it because miles and kilometers have a conversion factor as well. So we can convert miles into kilometers, but we'll do that another time when we start talking more about that. All right, how will we measure the mass of an automobile? What's our SI unit for mass? I heard somebody say it earlier.
Grams.
It's in grams, right? Grams, right? And when you have larger objects, you know, you might be talking about thousands and thousands of grams as opposed to tens or hundreds of grams. So once you get past 1,000, you can add a prefix, and we're going to talk about these prefixes shortly. Kilo. So we can measure the mass of large objects in what we call kilograms. Let me fix that because that case should be lowercase. Kilograms. All right. So we'll measure the mass of an automobile, something big like that. We'll measure it in kilograms rather than just grams because the numbers can get really, really big. So we want to keep those numbers manageable so we can put prefixes on to indicate a change in an order of magnitude, right? And we're going to talk about that down here in the next question about the numerical value of the prefixes. What about the volume of a swimming pool? How do we measure volume? Because volume is not one of our 7 fundamentals. So how do we measure volume? Volume is actually a derived unit. Right? It's derived.
Liters?
It's derived. Good.
Is it meters?
Good. Yes, it is. It's meters. Yes, it is. It's meters. But the fact that volume is three-dimensional.
No, liters.
It's meters. It's meters. Right? It's meters cubed. Because volume measures length times width times height. So we measure the volume of a swimming pool in cubic meters, or we could also measure it in cubic centimeters, which would be a much bigger number. Or we could use liters, which is the equivalent of a cubic meter. Or we can use milliliters, right? So a liter is the equivalent of a cubic meter. A milliliter is the equivalent of a cubic centimeter. And so we can use either one of those, but the fundamental SI unit is meters. So for volume, which is a derived unit, a derived value, it is meters cubed. All right. What about, let's go to the next one. What about speed? The speed of an airplane. That's also going to be a derived unit. This app is really getting on my nerves. Come on, man. All right, the speed of an airplane.
The meters per second squared.
Okay, great. You're in the ballpark. Meters per second squared is for acceleration. Speed is
Miles per second.
meters per second, because we're talking about SI units, right? So SI base units. So we want to use, for speed, we want to use distance over time. All right, so this is, in this case, meters per second. Good though. Thank you for chiming in. I appreciate it. All right, so speed is derived, volume is derived. What about density? Density is also a derived unit, right? So you're taking two units together, two SI units together. So for density, let me see if I can put some space here because this is getting jumbled up.
Would that be D equals M over V?
Come on with it. Yes. Density is mass over volume. So density is a derived unit. So density equals mass over volume. And that's going to be grams over cubic centimeters or kilograms over cubic meters. Either way, but we normally use this unit for density, grams over cubic centimeters or grams per milliliter. Both of those will suffice for the density value. Now, the thing about density, with it being derived, you can derive any one of those values from that equation. So if D equals M over V, V times D is going to be what? M. Is that right? Or if you want to derive the volume, V will be mass over density. All right. So anytime you have a derived unit like that, you can break it apart into its constituents and find any one of those substituents as long as you constituents, as long as you have two of them. So if you have mass and volume, you can find density. If you have mass and density, you can find the volume. If you have density and volume, you can find the mass. All right. Let's go to go to the next one. It says the area of a football field. How do we find area? Is that two-dimensional or three-dimensional? Is that right? It's 2D. So if the length and the width are in meters, the area is going to be in meters squared. Following? Yes, no?
Yes, sir.
All right. All right, let's go to, any questions about that before we go to the next one? All right, let's go to the next example. Excuse me. And this says, this is a kind of a two-part question. Give the name of the prefix and let me put some space here right quick, hold up. All right, it says give the name of the prefix and the quantity, because each one of those prefixes has a specific quantity associated with it. All right. So let's do the lowercase letters first. And we didn't get a chance to really hit this the other day in class. We're going to pull up the chart. Let me pull the chart up. So right here, we have our prefixes. These are the prefixes for any unit. You can put a prefix in front of it. And these are the numerical values. So for milli, it's 10 to the minus 3. For centi, 10 to the minus 2. Deci is 10 to the minus 1. And then kilo is 1,000. So 10 to the third. So milli is 1,000th with a th on the end. Centi is 1/10 or 1/100th with a th on the end. And then deci is 1/10 with the th on the end. And then the kilo is 1,000. Mega is 1,000,000, 10 to the 6th. Giga is 1,000,000,000, 10 to the 9th. And then tera is 10 to the 12th. So when you hear a measurement of a hard drive that's 2 terabytes, that means that there are 2 trillion bytes in a in a 2 terabyte hard drive, right? So million, billion, trillion, mega, giga, tera, and then milli, centi, deci is 1,000th, 100th, 10th, and then kilo is 1,000, right? So if I put K, the lowercase k in front of grams, 1 kilogram is 1,000 grams. 1 kilometer is 1,000 meters, right? So let's take that. I'm not gonna I tried to copy this in earlier, but I couldn't. So let's take that. Let's go back to our document here. And we have a lowercase c, which is what?
Centi.
Centi, good. And how much is that prefix? How much does that indicate? 10 to the what?
10 to the negative square.
2, yeah, 10 to the minus 2, right? Or 1/100th. All right, what about the D?
Deci.
Deci, good. And this is what? 1 what?
10 to the negative 1.
Yep, so it's 1/10. What about G?
Giga.
And how much is that?
10 to the
10
9.
to the 9.
10 to the 9th, so that's 1 billion. It's a lot. And then kilo is 1,000, right? So that's 10 to the third. And again, this is boring and redundant, but it's all reps, because when you work in problems, you're going to see these prefixes and they're not going to give you like, the problem is not going to say, oh, milli means this. So you have to learn the prefixes in order to understand what quantities you're working with. All right. So M is what?
Milli.
Milli. Right. And that is 10 to the minus what? Anybody?
3.
3.
Good. It's 1/1000. N, which we didn't see on the other page. Let me see if anybody knows what lowercase n is. Anybody?
Nano.
Excellent. Nano. So nano and giga are opposites, right? Giga is 10 to the 9th. Nano is 10 to the negative 9. So it's 1 billionth of something. Right. And now we actually have instrumentation where you can actually see on the nanoscale. You can see particles that have sizes in that range with some really specialized equipment and like SCM and TEM and instruments like that. All right, what about P? Anybody know that one?
Is it pico?
Pico, excellent. It is the opposite of tera. It's 10 to the minus 12 instead of 10 to the 12. So I just gave you tera, I just gave it away. This is 10 to the 12th, right? So it's very important, get that table. It's in the notes from the other day, and it's located in the course notes content area on Blackboard. Get that table and memorize those prefixes, because you're going to need them, right? Because the prefixes tell you basically the type of quantity you're working with. Or if you're working in milligrams, you know you're working at the sub-gram level, 1,000th of a gram. Just like we were talking about the other day, and this is not on here, but remember we were talking about ivermectin. What unit were we using? Anybody remember? We were using micrograms, weren't we? And that is the opposite of mega. So mega is 10 to the 6th, and micro is 10 to the -6. All right, let's look at the next one. It says a large piece of jewelry has a mass of 132.6 grams. A graduated cylinder initially contains 48.6 milliliters of water. When the jewelry is submerged in the graduated cylinder, the total volume increases to 61.2 milliliters. So this is, we're looking for the density right? And this is what we call a volume displacement problem. It's a volume displacement problem. So we're looking for the density. And we know that density is what? What's the formula for it again? Anybody?
Wait, how do we know that we're looking for density?
It gives you the mass, it gives you the volume. I don't know if part of this problem got cut off, but this is it. That's what we're looking for.
Okay.
When I copied it in, I may have left off the last piece, but let me do this. Let's write it in. Find the density of the metal. How about that? All right, so this is what we call a volume displacement problem. We don't know the volume of the metal itself. We have to derive it. And the way, remember when we talked about when you work problems, you have to ask what you have, what you know, what you don't have, and what you're trying to find. Right, so what we don't have is the density. Right, what we don't have is the actual volume of the metal, but we can find it based on the displacement. The initial volume is 48.6. The final volume is 61.2. So we can find the volume by taking the difference in those two numbers. So that's going to be 61.2 minus 48.6. Right? Somebody help me out with that. What do we get?
$12.6.
So 12.6 milliliters. Good. It's got 12.6 milliliters as the volume. We know the mass, right? 132.6. So we can put that into, I didn't finish this up here, sorry. This is mass over volume. So the density is going to be 132.6 grams over 12.6 milliliters. What do we get?
$10.5.
And that's in grams per milliliter. Again, the units are so important because without the units, We have no idea what that number means. All right, let me show you. This is actually, if you downloaded that ebook, there's a really cool density exercise here. And you can actually go in and use this volume displacement method to determine density, right? So we have a balance where we can find the mass. And then on the other side, we have a liquid that if we fully submerge one of these things, like a piece of gold, put it on the balance, that gold weighs, somebody write this down, 40.53 grams. That's the mass. All right. What's the initial volume in that beaker?
25.5 milliliters.
25.5. Now, when I put the gold in here and submerge it, watch what happens. What's the volume now?
27.6 milliliters.
So what's the difference in the volume? 25.5 to 27.6. The difference,
2.1 milliliters.
2.1 milliliters. So what is the density of gold? We know the mass, 40.53 grams, over the volume, which is what again?
Is that the 2.1 milliliters?
Yes. Take those two numbers and divide them and tell me what you get.
19.3 grams over milliliters.
19.3 grams per milliliter. Very good. Right. And you can do that with any of these. There's a link in the ebook in the section on derived measurements where you can play around with this little simulation. I think it's pretty cool. All right. So when we go back to, let's go back to our problem. Can somebody Google the question, what metal has a density of 10.5 grams per milliliter? Can somebody Google that real quick? It's not gold, obviously, because gold, we just said, was 19 point something. But it is a metal because it says jewelry, so it's got to be some type of precious metal. Unless it's fugazi, then it can be anything. Excellent.
Is it silver?
It's silver. Robbie also Robbie also put it in the chat that it's silver. Yes, it is silver. See that's an investigative method, right? If you don't have the actual identity of the metal, but you know it's a metal, and you find the density through displacement, you can do a little bit of research and find out what metal it is. So this is silver. All right, good, excellent. This is great. Any questions about that? So if you see a question like this on the test, if you have a mass and you're talking about submerging that object into a liquid and you have a volume change, then you can calculate the density. All you need is the initial and final volume and the mass. All right. We're going to skip number 6. We'll come back. We'll do that one tomorrow. Let's do number 7. Number 7 is about Sig Figs, and it asks, how many significant figures are contained in each of the following measurements? All right, so let's look at it. There's a method that you can use, and let me show you a picture of it first. It's in my email because I was looking at that earlier. Let me show you a picture of it first, and then I'll show you, which one is it? This one? Yes, it's this one. Can y'all see that?
Yes.
Yes.
Okay, so it says if a decimal point is present, you can use either what's called the Pacific method or the Atlantic method. The Pacific is what is on the California side. You see how they have the country with California on the left, and which is bordering the Pacific Ocean, and then on the right you have the Atlantic Ocean. So if there's a decimal point present, start on the Pacific side. If there's no decimal point, start on the Atlantic side. So on the Pacific side, if you draw an arrow, it says draw an arrow until you hit a non-zero digit. Right, so you see that the first number is non-zero. So that means everything after that, because of the decimal point, is significant. So you see the answer there is 6 sig figs. You look at the bottom one, it says, if there's no decimal point, use the Atlantic method and draw an arrow until you hit a non-zero digit. And that'll tell you how many of those digits are significant. In that case, it's 3. Do you see that? So decimal point, decimal, you use the Pacific method. No decimal, use the Atlantic method, and you draw an arrow until you get to a non-zero digit. All right, so let's look at I don't know if I can embed this in. Let me try. I'll download it to my photos and open my photos. Can I copy that? No, never mind. Never mind, I'll just keep it open. All right, so let's look at that first one. Is there a decimal point?
No.
No. So let's use it. We use the Atlantic method. So we're gonna go here. Uh-oh, need my brush here. The first digit is a non-zero digit, is that right?
Yes.
So 2 sig figs. Yes, no?
Yes, sir.
Both significant.
Correct.
What about B? Atlantic or Pacific?
2.
There's a decimal. Think of the P.
Oh, 1. Sorry.
Yeah, think of the P in Pacific as point. So if there's a decimal point, you will start from this side. Boom. The first non-zero digit I hit is 2. Is that right?
Yeah.
So everything after that 2 has to be significant. So this is 3 sig figs. Let's go back to the example and make sure we're on point. You see how for the Pacific method, when you come from the left, the first number is 1. So everything after that number is significant. Is that right?
Oh, that's like the sandwich rule. So if you have like zeros in between, but
Yeah.
if you have like a whole number behind it, then all those numbers are included.
Yes, excellent. You say the sandwich method, I like that. Let's do one. Let's look at one of the sandwich ones. There's one here, right here. As a matter of fact, if I draw an arrow, there's no decimal, so I have to come from the Atlantic side. If I draw an arrow, the first non-zero digit I encounter is 2. Is that right?
Right.
And the zeros that are there are trapped in between the 2 and the 6. So all of these numbers are significant. So this would have 5 sig figs. Are we following? Everybody okay?
Yes, yes, sir.
All right.
Can you explain B one more time?
B? Yeah, sure. So because there's a decimal point, when I hit that first non-zero digit, which is 2, everything after that becomes significant, right? So and the fact that the 0 here is trapped between the 2 and the 5, you see that? So I have to include that in the sig figs. I can't drop it.
So is the 10 to the 8th not a part of the sig figs?
Yeah, because, okay, so the 10 to the 8th means that there's going to be 6 zeros after that 5. So those are trailing zeros. So none of those will matter.
Okay, that makes sense.
Yeah.
So we're just
it'll be-
looking at the 2.05.
Yeah, so it'd be let's say 2.05 times 10 to the 8, right? So that'll be, we move the decimal 2 times. So now this goes from 8 to 6. So it's 2 0, 5, 0, 0, 0, 0, 0, 0. You following?
Yes.
So everything, when I get to here, everything after that is not significant because those are trailing zeros. They don't change the value of the number. That's a great question. Nobody this morning asked about that exponent. So that's a great question. All right, what about D? How many sig figs there?
Is it 3?
4.
Actually, for the decimal point is going to make the 0 here actually count. I can zoom in on that because it's included here. Highlight it, right? Just like if we were to include a 0 here, that decimal point is gonna cause that that 0 in this particular case to count. So that would be 4 sig figs. If we drop that 0, then it would be 3 sig figs. But because of the decimal point, we have to include it. All right. Everybody okay?
Yes, sir.
All right. Let's do what about E? Then we're gonna move on and do I want to do a couple, at least one of the conversions that we are gonna come up on. What
Be
about
6 figs, right?
6? Yes. Because if I do, because the decimal, I'm going Pacific here. First number I encounter is 1. So everything after that is significant. So it's 6. Good. Now right here, I have a decimal 2, but my first non-zero digit is after the 0, right? So this is 2 sig figs. And the same thing here. Boom. If I come to here, these are all significant. The leading 0 is not. So that would be 1, 2. No, let me take that back. All right. All right. Let's do we'll do 8 tomorrow. We'll do number 8 tomorrow in class. We got 3 minutes. So let's do this question right here dealing with accuracy versus precision. Accuracy versus precision. All right. So accuracy is the closeness to a standard value. Precision is a little bit different. So that when we talk about measurements, this is related to measurements. It's the closeness of measurements to each other. So measurements can be precise, but totally inaccurate. Or they can be both accurate and precise, or they can be neither. So let's look at the question. And for this particular example, the bullseye is the accepted value. So this is what we're trying to reach, right, in each case. So that's my accepted value. All right. So let's look at letter A. Says which archer is the most precise, not accurate, but precise. So in which one of these examples are the dots or the arrow marks after shooting the arrow as close to one another as possible?
X.
X. Excellent. Very good. So this is precise, most precise. Totally inaccurate because it's so far away from the bullseye, but very precise, meaning I hit literally almost the same spot every single time, right? So that my values are very close together, even though they could be far away from the desired value or the accepted value. All right. What about B, letter B? Which archer is the most accurate?
W.
W.
X.
Good. Right. This is the most accurate. Let me fix that. Because the accepted value again is the bullseye. So the closer I get to that, the more accurate I am. The further I am away from that, the less accurate I am. All right, what about C? Least precise and least accurate. Which one do you think?
Y.
Y.
What?
Y is both least precise and least accurate. Nowhere near the accepted value for the bullseye and nowhere near each other, right? So that would qualify that as being the least accurate and the least precise. All right, so we're gonna stop here. We're gonna bring this with you to class tomorrow because we're gonna do some more work with Sig Figs, and we're gonna do some more work with some unit conversions and some other calculations. All right, we're good. Everybody good?
Yes, sir.
Yes, sir.
All right. Thank y'all for you. This is great. Thank you for
Yes.
your participation. And God willing, I'll see you tomorrow at 1 o'clock.
I have a question.
Go ahead.
So I was gonna ask about, I know last time we did this, so I was gonna ask when the assignment due was.
Yeah, don't turn it in until we finish it.
Okay, no, not this one, the last one.
The last one, yeah, you were supposed to turn it in last Thursday, but if you haven't, it's still open. So go ahead and turn it in.
Okay.
Go ahead, Timothy.
Were we supposed to put our name in the chat?
Yes, I don't think anybody has logged, well, maybe some people have logged out, but yes.
I have a question.
Go right ahead.
That email that you sent us yesterday about the safety exam, is that due on Sunday?
I can't remember what date I put on that. Let me go back and look.
And like all those assignments that you listed, is it all due on Sunday?
Yeah, it looks like a lot, but it's really not. Are you in the Wednesday lab or the Tuesday lab?
The Wednesday.
Let me open up the announcement. Yeah, it looks like a lot, but it's not that much. It's the safety exam. I mean, once you read through the little safety document and take it, that's it for that. The Sig Figs assignment is one assignment, and then the what's going to take you the longest is going to be the Labster, the periodic table one. So yeah, these three things are due by Sunday. I didn't put a time on it though, so you really got all the rest of this week to finish them.
Okay.
Good
Thank you.
question. Yeah, you're welcome. Good question. All right, any other questions? All right, if
Hey,
not,
Doc.
go ahead.